Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to make a tax-deductible donation to support our students, please go to smarturl.it/help-ISU-actuary. Here is a problem for Exampie on probability. An insurance company issues 1,250 vision care insurance policies. The number of claims filed by a policyholder under a vision care insurance policy during 1 year is a Poisson random variable with mean 2. Assume that the number of claims filed by distinct policyholders are independent of one another. What is the approximate probability that there is a total of between 2,450 and 2,600 claims during a 1-year period? One important observation is that the expression approximate probability, that's a hint that you will be probably using the central limit theorem to solve this problem. And here's the solution. Let x1, x2, and so on through x 1250 be the number of claims filed by each of the 1,250 policyholders. We are given that each xi follows a Poisson distribution with mean 2. Because Poisson distribution has the same mean and variance, it follows that E of xi is equal to the variance of xi and is equal to 2. And we are interested in the random variable s equal to x1 plus x2 plus and so on up to x 1250. Assuming that the random variables are independent, we may conclude that S has approximately normal distribution because it's the sum of independent identically distributed random variables, each of which has a finite mean and variance, so S is approximately normal, with mean E of S equal to the variance of S as well, which is 2 times 1,250, so 2,500. Because the mean is a sum of the means and the variance is a sum of variances and for individual random variables, and each of the individual random variables has the mean and variance equal to 2. Therefore, the probability that S is between 2,450 and 2,600, which is what we're looking for, we're going to actually approximate it with a normal distribution, but it's an important thing to note that S is a discrete random variable because we obtain it as a sum of discrete random variables, and normal random variable is continuous. So we're going to use continuity correction, and for a discrete random variable, S being more than 2,450 is exactly the same as S being more than 2,450.5, but switching to the normal distribution, there will be a better approximation. That's the idea of using continuity correction. And the same way, S being less than 2,600 for a discrete random variable is exactly the same as S being less than 2,599.5, but when we switch to the continuous normal distribution, it will be a better approximation. Now we subtract the mean and divide by standard deviation, and this becomes 2,450.5 minus 2,500 divided by a square root of 2,500, which is the standard deviation of S, less than S minus 2,500 divided by the square root of 2,500, less than 2,599.5 minus 2,500 divided by a square root of 2,500, and we're looking for the probability of this happening. And that's equal to the probability that negative 0.99 is less than S minus 2,500 over 50, and that's less than 1.99. And that in turn is equal to the probability that s minus 2500 over 50 is less than 1.99 minus the probability that s minus 2500 over 50 is less than negative 0.99. It's actually less than or equal to, but because we're going to switch to the continuous distribution, it's not going to matter. So the point is that this s minus 2500 over 50 is approximately normal, but this is a random variable that has a mean of 0 and standard deviation of 1, so it's really approximately standard normal. So s minus 2500 over 50 is approximately standard normal, and if we denote a standard normal random variable by z, what we basically have is that the probability we're looking for is approximately equal to the probability that z is less than 1.99 minus the probability that z is less than negative 0.99. And that's the probability that z is less than 1.99 minus 1 minus the probability that z is less than 0.99, and we get those two approximate probabilities. The probability that z is less than 1.99 is approximately 0.9767 from the table, or some other way of calculating the probability for a standard normal random variable, and then minus 1 and minus, so plus probability that z is less than 0.99, which is approximately 0.8369. Once we plug those values in here, we have them, we just do the calculation. This comes out to be approximately 0.8136, which is answer B. Please remember this is copyrighted material. The problem itself comes from Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.